Okay, we're going to look at another example using this part of the fundamental theorem of calculus. So I erased the other part here so that we can just focus on this part for right now. All right, and then we have another problem over here. Not too much different from the last one we looked at, but different in a couple of ways. One, the lower limit of integration is a different number. And two, the upper limit of integration, instead of just being x, is a function of x, which is an important difference to pay attention to. All right, so this part of the fundamental theorem of calculus says if our function f of x is continuous on AB, here our function f of t instead of f of x, but f of t is e to the t squared, which is continuous everywhere, then the derivative with respect to x of this integral from a to x, f of t dt equals f of x. And so we have the same function here, little f, but instead of being evaluated at t, is evaluated at x. All right, so one important thing about that is notice that in this result over here, I don't have anything involving the a. So the fact that this is starting at pi instead of at 0 is actually unimportant unless perhaps my function was not continuous everywhere, and then I would maybe need to make sure that it was continuous on the interval that we were interested in. What is important, though, is that I don't just have x up here in my upper limit of integration. I actually have a function of x. So I'm going to actually be using this part of the fundamental theorem of calculus, but then I'm also going to be using something that it's been a while since we've used, but shouldn't be that far from your memory because I think everybody knew it pretty well when we learned it. All right, so this part of the fundamental theorem of calculus says we're going to have the same function, in this case e to the variable squared. So e to my variable squared. And then instead of the input being t, though, our input is what's up here, x. All right, so in this case, instead of what's up here, x, we actually have sine of x. So I'll have that here is the input for that function squared. All right, now remember that we're differentiating, and so that step of differentiation essentially took care of the derivative undoing the integration part. But because I have a function of x here in this limit of integration, I'm actually going to need to use chain rule. So here, instead of just having x, my function here is really a function g of x, and then we know from chain rule that we would have that times g prime of x, right? So this is combining fundamental theorem of calculus, but instead of just an x there, we have a g of x as our limit of integration, provided that's a differentiable function. We're going to have this times the derivative of that function. All right, so the derivative of sine, hopefully you remember that. Didn't forget that one, right? Derivative of the sine function is the cosine function. All right, so here's our answer. I might tidy that up a little bit. Maybe I'll put the cosine function in front. Cosine of x times e to the, maybe I'll write that as sine squared of x. All right, so that was just combining this fundamental theorem of calculus along with a little bit of chain rule right there. All right, so there are a few homework problems like that.